here to share some of the work that we've been doing at NASA on the ATD2 or the Airspace Technology Demonstration 2 project. One of the reasons I'm so excited, as Raj kind of alluded to, it was less than 10 years ago that I was working on some problems on the surface of the airport, and there was no data available in this one particular domain of the airport called the ramp area. There was so little data available such that I had to develop a scaled down robot experiment to produce data to examine and to build some models with. Nowadays, less than 10 years later, which will be a main focus of this talk, we have an explosion of data that's available to us as scientists. And it's just a really exciting time to get to work on these type of problems. So to kind of level set us and give a little bit brief explanation what ATD2 is, I just wanted to play this quick movie, but there we go. Okay. So we're having a little bit of challenge here. It just, okay. Okay, perfect. Okay, so we'll start this over. Okay. Yeah, and then we'll get some volume. Okay. Okay. There we go. Okay, so that video gave a little bit of background about what the Airspace Technology Demonstration 2, or from now on, I'll probably just refer to it as ATD2. And then this is the full kind of concept. So the idea here is ATD2 is the name of the project, but the name of the tool that we developed is called IADS, which stands for Integrated Arrival, Departure, and Surface Traffic Management. And so that video showed a little bit of background about what we're doing at Charlotte Douglas International Airport, which is a major US airport. I believe it's the 7th busiest airport in the world by the number of aircraft that move in and out of Charlotte on a yearly basis. But what we're doing at Charlotte is kind of more analogous to what you're seeing here, where there's a single airport and there's challenges in integrating the overhead stream with the surface of that single airport. And you have to create this kind of coordinated schedule between the arrivals, the departures, and all of the surface traffic. So that's kind of the ATD2 concept in a nutshell there at Charlotte. However, the ATD2 concept can actually be extended to kind of to what you see here in this picture, which is multiple airports interacting with each other in what we call a metroplex environment. And so now you still have to manage the arrivals and the departures and all the surface traffic, but then you also have to have some kind of coordinated scheduling going on here at the terminal boundary. And what can happen essentially, as you can imagine, is, weather could come in and constrain the capacity here. And then all of a sudden now you're in a situation where you have a demand capacity imbalance of the terminal fixed, and you have to think about how to kind of try to solve that problem efficiently. And so, the purpose of today's talk isn't to go too deeply into the concept, but we wanted to give a little bit of overview of what the problem we're trying to solve on ATD2. And the thing that I really like about that video that I showed earlier is that ATD2 is not just research that lives in PowerPoint slides and in research papers. We have developed a tool, we have fielded that tool, and now we're going through a 3-year field evaluation that started in September 2017 and will end in September 2018. During this field evaluation, we've produced the benefits that you see here on this slide. So because this tool is not just research that's living in research papers, what you can see here is that through what we call departure surface metering, which when there's a demand capacity imbalance, we kind of hold departures back at the gate with engines off to reduce the amount of time that they spend in the departure queue with their engines running. And through also integrating the surface with the overhead stream, through those two capabilities, we estimated that just at Charlotte, so a single airport, since September 2017 until essentially the end of January 2020, we've saved roughly 4.4 million pounds of fuel. That 4.4 million pounds of fuel is equivalent to planting over 100,000 urban trees. We just hit this kind of benchmark of 100,000 trees within the last couple of weeks. I think we all are really excited about that. In addition, we estimate that we've saved over 550 hours of delay, which could be converted into roughly about $2.6 million of passenger value of time and $750,000 in flight crew costs for the airline operators. And then overall, we've also estimated that we've saved about 3,300 hours of reduced runtime on the engine. So again, ATD2 is creating these coordinated schedules between the arrivals, the departures, and the surface traffic. And through this coordinated schedules and the predictability, we're able to reduce fuel consumption and CO2 emissions, which I think is something that we're really excited about and looking forward to seeing this tool progress. One thing I forgot to mention is that ATD2 is the predecessor of an FAA tool called the Terminal Flight Data Manager that will get rolled out to every major airport starting in 2020. So we went through this 3-year field evaluation as essentially a prototype. We tried to learn lessons, and then we try to pass all the lessons we've learned onto the FAA as they begin to implement their tool across every major airport in the country. So, we talked a little bit about ATD2 and the types of problems we're working to solve and the benefits that we're seeing from solving those problems. But, the question can become, well, how are we actually, creating these coordinated schedules? How do we create this efficiency? How do we create this predictability? And the answer is that the backbone of the ATD2 system is what we call system-wide information management, or SWIM. So you'll probably hear me use that acronym. So SWIM is a digital data sharing infrastructure. The idea here is that SWIM is this FAA cloud that is distributing the data in real time to users of the National Airspace System and providing the data and the answers that they need to make operational decisions. So the idea here is that the FAA systems and other systems are producing all types of data, whether it be weather data, whether it be flight data, other types of aeronautical data, en route data, which is, when you're flying kind of at 35,000 feet, and then also this surface movement area data. So we have all these different data sources, And what happens is previously in, not even that long in the past, that all these FAA systems were kind of isolated and they were connected in point-to-point connections with each other. And they all each kind of like controlled their own domain, but they didn't release that information outside of their own systems. And so it became very difficult to know kind of what this other FAA system thought about a flight unless you were directly connected to it. So now all that data gets distributed to the cloud. And then from the cloud, that data can be consumed by all these different consumers. And so this has really enabled a lot of new technologies to drive efficiencies throughout the NAS. And this is essentially kind of the architecture that is enabling the next generation of kind of air transportation. So again, SWIM is the system-wide information management. That is the FAA's cloud. And there's this thing called the SWIM Industry FAA Team, or the government likes to do a lot of acronyms, and this is actually an acronym in an acronym, which is unusual. But these are all the stakeholders of SWIFT. So SWIFT is the SWIM Industry FAA Team. And what you can see here is there's a significant amount of users for this SWIM data, whether that be airlines, whether that be government organizations, whether that be vendors, trade associations, or some type of support organization. And so there's this whole community out there that is now, just now getting access to this digital data that's in the cloud. And everybody is really excited. Everybody in the industry is thinking, how can we leverage this data to do amazing things? What types of things can we do with it? And, everybody thinks, okay, well, I have this cloud. I can I'm an organization, imagine that I'm, United Airlines. And I say, okay, I want to connect to this cloud. So all I do is connect. I start consuming data and things are great. But in reality, there's a significant amount of challenges to connect to SWIM and to consume the data from SWIM. It's not nearly as easy as you would think. And just to kind of share some of the tip of the iceberg challenges is that SWIM has huge volumes of data. The velocity of the data is also extreme, which is that the data is coming at you very, very fast. It's not just that there's large data, it's coming at you very, very fast. And then moreover, the data has a significant amount of variability to it. What do I mean by that? Is that on the previous slide, we showed that there's all these kind of individual data sources that are producing data and distributing them to the SWIM cloud. Each one of those data sources is consistent, within itself. The problem is that those data sources aren't consistent with each other. What do I mean by that is that one data source can talk about flight XYZ100 and have some unique identifier for it. Another data source might talk about flight XYZ100 and have a completely different unique identifier for it. So you're consuming the data from SWIM, and all of a sudden you're left to think, how do I make sense of this data when it says, how do I know that from this data source and from the other data source that they're talking about the same flight? And that becomes a significant challenge for all of these organizations when they think about connecting to SWIM. So again, the volume, the velocity, and the variability of the SWIM data create significant challenges to consume this data. So to address some of these challenges, NASA has invested in this technology that we call the fuser technology. The main idea here is that the fuser technology, you can imagine, as we showed, that there's all these different data feeds coming in. Again, each data feed is consistent within itself, but for example, this top data feed might be inconsistent with some other data feed, even though within themselves, everything makes sense. So NASA developed this fuser technology that's able to fuse and mediate the data sources. And so not only are we able to create a consistent view of a flight to say, well, now that we have these multiple data sources, we know exactly when each one of them is talking about XYZ100, but there's also higher level logic there that we've also applied in the fuser, which is that these data sources can have different quality of data. What do I mean by that is one data source might have higher quality of data than the other, but the higher quality data might not always be available. So you have to create these rules that would say, well, I would always select data source A if available. However, if not available, I'll select data source B. And that might seem simple enough, but it actually could even become more complicated where the data source that you want to select can be dependent upon the state of the flight. And so all these challenges, all these complications, each one of those Swift stakeholders that wants to connect the swim and consume the data has to face this challenge. And so us at NASA, we said, okay, well, we don't want every consumer that goes and tries to connect the swim to have to reinvent the wheel, to have to kind of have all this domain knowledge to understand how to fuse and mediate between the data sources. So we invested in the fuser technology, which, as I said, takes in all the data sources, fuses them, creates this consistent view of a flight. That data is then fed as input to the ATD2 IAD system. And then now the IAD system, makes predictions, makes calculations, computes answers. It has additional data that's not necessarily available in the swim feeds. All that data then is sent out of the IAD system and distributed back into the swim cloud so that we can make our data, our answers available to other users of the NAS. So now that we understand what the fuser technology is and kind of how important it is to create this consistent view of a flight, this is what the full ATD2 data architecture looks like. So again, we have this swim cloud here. This is the FAA cloud where all the data is. So what's happening here is that the swim data is being sent as input to the ATD2 IAD system. We also have additional data sources. So we have connections for the field demonstration that we're running. We have connections to airline operators' data sources as well to provide some data that might not be available in swim. So we take the swim data, we take these other data sources, we send them to the fuser. They go to, here it's labeled as STBO, which stands for Surface Trajectory-Based Operations, but that's the IAD system. The answers that are coming out of the IAD system get written to a database, and then the answers get sent back via what we call the TTP feed, the TFDM terminal publication feed, and get sent back to swim. Moreover, because we're sending all of our answers to these databases, we can create these post-ops view of the operations, which we call the flight summary files, and we generate them and have them internally here at NASA, but we also send them to the airline. And then similarly, once we've created this fuser technology, right, we don't want to be the only ones that have access to it. We actually are trying to open source the fuser technology and give it away to the community. And so what the other thing we've done is we've created this idea of what's called Fuser in the Cloud. And Fuser in the Cloud is essentially doing the same type of idea where it's taking in the swim data, it's fusing them, and then the airlines can directly consume these fused data sources from the cloud. And so this is kind of the full ATD2 data architecture. And the key idea here is once you understand the fuser, you can understand this idea of the fuser in the cloud. So what does fuser in the cloud enable? Fuser in the cloud enables these, what we call real-time services powered by the swim. Again, the swim is the cloud. So the idea here is that you have all these FAA systems, you have this FAA cloud swim, and once you have Fuser and you can create this consistent view of a flight, now what you can do is you can start to think about developing services. What do I mean by services? Think about a prediction, like, some airline operator has a question that they want answered, or they want a prediction of something, like, let's say, congestion, right? If the airline operators know where the congestion is, they can think about routing around it. So the idea is that once you have Fuser in the cloud, then you can create these real-time services in the cloud. You can compute the answers, compute the predictions, and then you can distribute those answers, those predictions, via the cloud to consumers that need those answers. And so what it enables is this real-time decision support, essentially, that's powered by this fuser in the cloud, and ultimately from this cloud, and all the data being accessible in near real time. And so, I think that we are really excited about this opportunity because there's a lot of inefficiencies that, if you just had the data and you had the data at the right time, you could probably shave a little bit of delay off. And when you're talking about these airline operators, it doesn't take much, a couple minutes of delay here and there, but then multiplied across their entire network. And we're talking about significant savings for them. And so this real-time services powered by SWIM is an idea that we have a lot of excitement about. And the way I think about it sometimes is essentially just this software layer on the other side of SWIM that's taking in the data, computing answers, and then distributing them via the cloud to consumers that want those answers. So, we talked about kind of these real-time services that are powered by SWIM, and it's nice to kind of think about this. And however, it becomes a little bit, high level and nebulous, like what are we really talking about? So now let's talk about a specific use case of a service that we think could drive some type of efficiency in the NAP. And so the example we're going to use for the remainder of this talk is a gate conflict prediction. And so what do I mean by gate conflict? I'm sure everybody here that's flown has had this experience. You are arriving at an airport, you touch down, you taxi to your gate, and all of a sudden you look out the window and there's another aircraft on the gate. And so that is what we would call a gate conflict. And so your arrival aircraft can't enter the gate until that departure pushes back and makes that gate available for it. So, a gate conflict occurs when the arrival touches down and the predicted in time overlaps with the predicted out time of the departure. These gate conflicts increase workload for the ramp controllers and could reduce the effectiveness of departure surface metering. So departure surface metering is, one of those mechanisms that we're saving the fuel that we talked about in the very beginning, and we hold aircraft at the gate with engines off as opposed to letting them sit in the departure queue with their engines running. And so the gate conflict could reduce the effectiveness of that, because if you have the arrival burning fuel and the departure sitting at the gate, you're not really saving much, right? And so as the metering unfolds, the relationship between the arrival and the departure banks can increase, decrease the potential for the gate conflicts. So we'll talk a lot here in a minute about what we mean by this, but just take this for granted right now. And then ultimately, we think that a near real-time prediction of gate conflicts could be used to provide some type of web-based alert to support decision-making to help improve the efficiency on the surface of the airport. So for this analysis, what we're going to do here is, as I showed the ATD2 data architecture, we're going to leverage these flight summary files, which are this post-ops view or post-operations view of the data. So for the remainder of this talk, we'll kind of talk about data that's available to us via this flight summary file. Okay, and so to level set everybody, this is the Charlotte Airport. So this is the airport that the Airspace Technology Demonstration 2 is being implemented at. And so just to give a little bit of background, we have these 3 parallel runways. We have this 4th diagonal runway. However, recently the FAA has began to move away from what they would call converging runway operations. So mainly now, the only runways that are in use are just these 3 parallels. On the left-hand side is an arrival-only runway. The runway in the center is predominantly a departure-only runway, although it could accept some arrivals. And the runway on the right-hand side is what we call a dual-use runway, which means that it accepts both departures and arrivals. So as I had mentioned, Charlotte is the 7th busiest airport in the world if you count it by the number of operations that happen at Charlotte yearly. And if the kind of poster child example of Charlotte is that it has the runways of a major international airport, but it has the ramp area, where the ramp area is this gray area surrounding the terminal. It has the ramp area of maybe like a small regional airport. And so you have all this traffic coming in like a major international airport, and then you have the gate capacity, or you have the ramp area or real estate around the gates that wasn't necessarily built to accommodate all this traffic. And what this creates is very challenging situation on the surface of the airport. We briefly also mentioned just the main capabilities that we have here for the ATD2 IAD system. So again, data exchange and integration is this idea of the swim cloud. So this is really the backbone that enables the entire ATD2 IAD system. We have departure scheduling for overhead stream insertion. So this is how we connect the overhead stream with the surface of the airport. And then we have departure surface metering, where we hold aircraft at the gate with engines off to reduce the amount of time they spend in the departure queue with engines running. So just to illustrate kind of the scale of the challenge here, this is a video from just a short period at Charlotte. And what I want to show here is you'll see things look pretty benign, not a lot's going on, but pretty soon here you'll see the traffic just comes out of nowhere and explodes. And then it gets really complex here. And the amazing thing is that air traffic controllers and Charlotte ramp controllers deal with this every single day, and they're able to handle this in an efficient way. And when you look at the complexity of what's going on here, you can see that surface management is challenging. You have all these arrivals, you have all these departures. They might need to go to opposite sides of the airport, which means that they need to like kind of go against the flow and streams here. And it's just a major challenge. On top of that, what we had talked about before, which enables all of these benefits, is that we need to create a coordinated schedule for arrivals, departures, and surface. So think about trying to create a coordinated schedule for the departures when you have this much complexity on the surface. And so this is really kind of an illustration of the challenge we face when we kind of try to integrate the surface traffic with the airspace. And personally for me, I've worked on the surface since probably 2012. And this is what really excites me, is that it's a challenge. It's not just something that, we can get a perfect answer in. It's like there's a significant amount of uncertainty. And so you have to be clever about how you handle that uncertainty to do things efficiently. So now the idea here is that we have this very complex traffic at Charlotte. We have all this data. And so what we want to do is we want to use the data to understand what's going on in Charlotte. Once we can understand what's going on at Charlotte, then we can maybe think about trying to predict what's going on at Charlotte. And so the first thing we'll show here is the horizontal axis is time. The top graph is what we call the excess departure taxi time. So that is the amount of time the departures are spending taxiing on the surface of Charlotte. But then we subtract out what we call the unimpeded or undelayed taxi time. So the excess taxi time is really kind of a nice way for us to say delay on the surface of the airport. The middle chart here is the average arrival excess taxi in time. So again, this is kind of the excess taxi time for departures. This is the excess taxi time for arrivals. But what I really want you to focus on is the bottom graph, which that is the count of operations, or the demand. And it's a stacked bar chart. And for this graph, this is a view of the demand based on the runway usage time of the departures and the arrivals. So each bar here is a 15-minute interval, and an aircraft gets placed in that bucket, that 15-minute bucket, if it uses the runway within that 15-minute bucket. And so what we can see here is that there's these concentrated time periods of demand. This is what we call a bank. So a bank is the concentrated time periods of demand. I'll try to take questions. Did you have a question? Can I hold to the end? Just because I have so many slides there. So this concentrated time period of demand is what we call a bank. And what's really interesting here is that if you look, say, at 12 o'clock noon, you can see that if you have this runway-centric view of the operations, that the departures and the arrivals use the runway at the same period of time. So again, at 12 o'clock noon, where you see the blue is the departure demand and the orange is the arrival demand, at 12 o'clock noon, when is essentially the peak demand period, there's almost an equal amount of departures and arrivals that are using the runways at the same time. This time periods of high demand lead to these large excess taxi times. So this concentrated time period of demand is what we call a bank. Similarly, as I had mentioned though, that was the runway-centric view. So you can take another view of the Charlotte operations, and you can say, well, I want to place an aircraft in my 15-minute bucket, not when it uses the runway, but instead when it either pushes back from the gate or arrives at the gate. So this is more of a gate-centric view of the operations at Charlotte. So what can we see here is that, whereas the departures and arrivals are using the runway at the same time, which we showed on the previous graph, if we come down, so this is the same graph where this is the departure excess taxi time at the top, arrival excess taxi time in the middle, and then count of operations at the bottom. Again, departures are blue, arrivals are orange. What you can see here is that if you take this gate-centric view of the operations, that the operations follow a more cyclical pattern where departures are the first ones to push back from the gate. So you can see here around 11:30 or 11:15 where you have the peak departure demand, there's almost barely any arrivals that are arriving at the gate. And then as the departure demand dwindles, that's when you start getting peak arrival demand for the gate. And so, you need this because you need the departures to push back to create the available capacity of the gate for the arrivals to come in. And so when you put these two things together, there's this coordinated dance going on between the arrivals and departures, which is that the departures start to push back from the gates. They move towards the runway. The departures are using the runways at the same time the arrivals are landing. And then because the departures have began to push back from the gate, it creates this available capacity for the arrivals to kind of move in there and use the gate. So one other way that we can look at this kind of view of demand at the gate and kind of see this cyclical pattern is here the blue is the departures and the green is the arrivals. And again, this is just a count of demand in 15-minute buckets. So it's the same kind of data, but just looking at it a little bit different way. And what we want to kind of illustrate here is that we see, this second blue peak right here, which is that when the departures are pushing back from the gate. And so what could happen is this arrival bank that is illustrated here with this green peak just below the green arrow, is that if this green arrival bank happens to come early and shifts to the left, what do you have? You have a demand capacity imbalance at the gate, and that creates gate conflict. That creates a situation we've all been a part in, that you're an arrival, you touch down, you look out your window, and you see another aircraft sitting at your gate. And so this is the kind of phenomenon that creates these gate conflicts. And what we've showed here is a little bit of our descriptive analysis to try to understand gate conflicts. One last thing here is that, we talk about bank operations, or we talk about the banks at Charlotte, which are these concentrated time periods of demand. And it's very easy for us to look with our eyes and say, okay, I see the concentrated time period of demand. But we actually need some automated way to define banks and to detect banks and things like that. And so what we did is we used a clustering algorithm that kind of automatically clusters the demand into these kind of distinct banks, right? And now aircraft is assigned to a bank if it operated within that kind of distinct cluster of the demand. This is kind of a simple example of machine learning that has provided enormous benefit to ATD2. Why do I say that it's provided enormous benefit to ATD2? Is because if you go and you sit down with Charlotte personnel that work the traffic in Charlotte, they think and they talk in banks. If you ask them, how was the traffic today? They would say bank 2 was horrible, bank 3 was good, bank 4 was okay. And so we needed a way to be able to talk the same language as the operational personnel at Charlotte. And this automated clustering of the demanding of banks enabled us to do that. So the remainder of the talk, which I'm going to try to leave a little bit of time for questions. So I have about probably 8 minutes, I'm guessing, here to get through. The remainder of the talk will be to describe this kind of workflow that we use. So far, we've talked about some of the descriptive analytics we've done to understand what's going on at Charlotte. Now, this is the workflow of taking our flight summary data, processing the data, and then this iterative process of feature engineering, model fitting, model validation, and then evaluation by a subject matter expert. And through this iterative process, we hope to develop a model that we can eventually deploy to the real-time system. The model I'll talk about today is not the model that we would deploy to the real-time system, but it's essentially a step in the right direction. We like to think a lot about this model of crawl, walk, run. So this would be the crawl in that process. So the idea here is once I have these banks defined, well, what can I do is I can start aggregating my demand and my metrics at the bank level to create something like this. So for example, on January 12th, 2019, Bank 2, we were in a north flow operation. We had 145 total operations, 75 of them were departures. We have all these other metrics as well. And then this data will become the features in our machine learning model. And then on the right-hand side, we have these regression targets, which is the count of gate conflicts. And then also we could take that count of gate conflicts and divide it by the total number of arrivals in the bank to get some type of almost normalized view of the gate conflict. So we also try to predict that target as well. One thing that I would mention is the data we're using is not purely swim data. Some of it happens to be answers that are coming out of the ATV2 IAD system. And some of those data elements, for example, about even the knowledge of a gate conflict is not necessarily available in swim. So that's unique data to the ATV2 IAD system. And then one last thing to mention is that, so when we have these features, we have these targets, before we start feeding this data to models, we normalize each feature by subtracting the mean and dividing by the standard deviation, such that you can imagine each column will have a mean of 0 and a standard deviation of 1 once we are done with that normalization. So the first thing is, well, we want to, do some simple tests to try to figure out which features are useful, which features aren't, which features should we keep. So in our work here, we considered 2 different models. One was a gradient boosting model. So we used gradient boosted decision trees. And then also we did a support vector machine. Both of these are regression models. On the left here, what we're showing is for one of our targets, which is the gate conflict divided by the number of arrivals, we're showing here the importance of each one of our 37 features that we consider. And so the idea here is not to care too much about what these features are, why are they important, that kind of stuff. But the thing is that when you look here, like let's say the support vector machine, you can see that some features have essentially 0 importance. And what can happen is if you have a feature that is not very predictive of your target and you include it in your model, what you can do is you can just essentially inject noise into your model. And so you want to try to eliminate some of these features here that are not very predictive of the targets. And so how can we do that? Is, well, for the remainder of this, as we kind of show what we're doing, we're always going to tell you which libraries we use because, the key thing is here is I'm not inventing new techniques. I'm just using scikit-learn. And the main job as me as a data scientist is actually to package the data into those tables that I was talking about with the features and the targets. And then scikit-learn makes it very convenient to do all this stuff. And so what we do is we do this kind of recursive operation of we fit our model. We use cross-validation to assess the accuracy. We identify the least important feature, we throw it out. Then we fit our model. We use cross-validation to assess the accuracy. We identify our least important feature and we throw it out. And we do this recursive process, and then we can identify kind of the features that we want to use. So you can see here when we did this on this data that we kept the top, 26 or so features and 23 or so features. These are the top graph here is for the just vanilla count of gate conflicts. The bottom here is that gate conflict per arrival. And so that is what we did using the scikit-learn, what they call recursive feature elimination using cross-validation. So once we have our features, all of these kind of machine learning models always have all these parameters to them. And, once you kind of hone in on a model, and you kind of decided on the features that you want to use, then the job becomes kind of like analogous to kind of just like polishing a rock or something. We want to tune all of these parameters to get the best performance from our models. So to tune the hyperparameters, again, we use scikit-learn, this grid search CV. And so it's about as simple as you can imagine from the name. We just do a grid search over all the hyperparameters, and we assess the accuracy using cross-validation. Here, we're showing the gradient boosting model in blue, and then a couple different flavors of the support vector machine where they could have different kernels. The main idea here is, though, again, we don't have to get too far down into the details. We have all these parameters. We just create a grid search over all the parameters, and we test out each one and assess the accuracy until we kind of find the best combination of parameters that gives us that best accuracy. So once we have our models, once we have the best combination of parameters, now we can assess the accuracy. And so these are kind of two values of accuracy that we kind of considered here. On the left-hand side is the negative mean squared error. And on the top will be the count of gate conflicts. On the bottom is that normalized gate conflict per arrival. On the right-hand side is the R squared or explained variance. And so the idea here is, again, we don't need to get too far down into the details, but what I will tell you is that if we used a naive prediction rule of just predicting the average number of gate conflicts, we would expect our negative mean squared error to be minus 1.0 because we normalized the target beforehand. And given that we see our negative mean squared error to be greater than that, that indicates that our models are doing better than predicting just the average number of gate conflicts. Analogously, when we looked at our R squared here, again, if we were to predict just the average number of gate conflicts, we would expect our R squared to be 0, but you can see that we have an R squared greater than 0. And so again, this indicates that we have our model is an improvement to a naive prediction rule that simply predicts the average. So to wrap things up here, we'll talk a little bit about future work. So the main idea for future work is we want to try to transition this gate conflict prediction model from post-ops to near real time. That comes with all these different complications, such as how to define a bank and implement the automated clustering of banks in a real-time environment, how to deploy the model to a real-time environment such that the answers can be made available in the cloud, how to make the model general such that it doesn't rely on data generated by the ATD2 IAD system, because if you want this model to scale across the national airspace, it can't use data from the ATD2 IAD system. It has to use data sources that are available at every airport. Other kind of future work is identification of additional use cases that can be leveraged, that can leverage the swim data in near real time to help drive efficiencies. Some examples of that would be prediction of the runways that arrivals or departures are going to use, or the flow direction of the airport. So typically airports operate in one direction or the other depending on sometimes wind. And so trying to predict that could help improve efficiency of the NAS. And then lastly, we're thinking very hard and working very hard to figure out how we can release publicly available data sets such that others can build upon and improve the work done by NASA. And so, I'm showing you some examples of the accuracy that we were able to achieve. Our hope is we could give you the data and you all could beat us, and that we would consider that very success for us. And so I think that's the end of the talk. And with that, I can take any questions. Yes.
Towards scaling this nationally, what do you see the challenges are in terms of customizing this per airport? Because I assume the surface configuration per airport is different. And likewise, they probably have different operational procedures, not to mention language that they use, especially trying to leverage the predictive positive outcome of your model, which seems to be
Yeah.
a
So
great result.
yeah, you hit on a good thing there, which is that so in terms of the banks aren't necessarily intrinsic to the geometry of the airport. The banks are more intrinsic to the fact that Charlotte is dominated by American Airlines traffic, and their network scheduling is the banks. And so different airports that are dominated by different carriers might have different structures to the data. So exactly right, which is that, when we think about the banks at Charlotte, that might not be applicable to each site across the NAS. But I think in general, we try very hard to come up with solutions that can scale across the NAS. And so, as I had mentioned, we view this as like the crawl in a crawl, walk, run. And so, just to begin with, we want to see if even with the best data available, can we do something good? If we can do something good, then we can try to improve upon it and figure out how to make it scale. But we just wanted to see if we could even make prediction right now. But very, very sharp.
So you mentioned before that you had weather data integrated into IADS as well. Is that being used? Was that used as one of the features for this prediction or not yet?
Weather data is integrated into SWIM, but we don't use weather data in the IADS system. However, when the weather during time periods of inclement weather, what happens is the air traffic controllers will put restrictions on the system, and that is actually what impacts the capacity, which then impacts delays and stuff like that. All the restrictions come through to us. So it's like we don't necessarily know it's raining, but all of a sudden when 50 miles of trail comes in over some fix, there's some inclement weather or maybe some capacity issues and stuff like that. So we don't directly ingest the weather data. However, some of the downstream impacts of weather, such as restrictions, we will ingest.
Got it. Thanks.
So regarding the actual choice of Charlotte Airport, I was just wondering what the selection criteria were for choosing that as a data set, like whether that be just the availability or complexity of data or the actual geometry of the airport.
So the Charlotte Airport was selected not just for the data set, but for the A32 IADS demonstration. And those decisions go much above my pay grade. But I think that Charlotte is a unique opportunity because it sits in this very special place where it's right on so air traffic is kind of at the top level centers, and then it goes down to TRACONs and like airports and stuff like that. So Charlotte sits right on the boundary of Atlanta and Washington Center, and it has a lot of overhead stream traffic that's going into what we call the Northeast Corridor, which is like New York area, New York Metroplex. And so what happens is that roughly about 10% of our departures from Charlotte are what we call controlled flights, which means that they have to merge into this congested overhead stream, and they have to get a very specific time window of 3 minutes when they're allowed to take off to merge into that overhead stream. And because of these unique constraints of overhead stream, in addition to the surface constraints, where I was saying Charlotte has the runways of a major international airport with the ramp area of a regional airport, that I think the combination of those two things led Charlotte to be almost a perfect, place to do this prototype. But like I was saying, that we're going through a 3-year prototype, and then the FAA tool, which the IADS system is a precursor to, will start to get rolled out to every major airport. And actually, Charlotte's the very first one on the FAA's list. So we're trying to make that transition as easy as possible.
Jeremy, this is Fritz. I have a question. I was wondering, has anyone thought about standardizing the input to SWIM so the producers of data, instead of having to use a fuser after you get all the data? It seems like it would be more efficient if everyone was, submitting standardized data that would allow the data to be tracked, if you know what I mean.
Yeah, I would say that if you want to change it, a lot of the data sources are coming from FAA systems, and to get anything changed within an FAA system is a major process, a major expense, and that I think that our view is that we're trying to think of ways to do as much as possible on the other side of swim so that we can remain more agile as we move forward. And so if everything relies on the FAA to make a change, I mean, you might only need one line of code to change the FAA system, and that could be 7 years and $100 million. That might be an exaggeration, but you kind of get what I'm saying, right? So the idea is that we want to remain agile on the other side of swim to kind of respond to challenges.
Okay, thanks.
So my question is, if you distribute this data to airport operators, and each operator optimize their operations, and then they submit that to the system, and how you will manage this system and how you will prioritize this operations? So
I mean, the airlines are optimizing their network schedules, right? So they're doing this already. So I think the airline operators are essentially trying to do this right now. We take in all of their data, right? And so, and then how do we prioritize them within like our coordinated schedules? So the way that we prioritize them is that the airline operators kind of got together and they all agreed that they wanted to play this game, which they call ration by schedule, or maybe first schedule, first serve. And the main idea there is that for airlines that have a scheduled ticketed time earlier, they get precedence. So like if the aircraft is already kind of delayed, it gets precedence over some other aircraft that is kind of not delayed. And that's kind of the rules of the game that they all agreed upon when we developed these coordinated schedules.
Jeremy, this is Gano. So is there some...
Jeremy, I have a question. I was wondering if the gentleman at the back was asking about airports.
Maybe it's not working. Yeah, it's probably not working. I can ask.
Anyone looked at the idea of coupling this data stream with a digital twin of an airport, so that we can then actually, it would become like a simulator of the airport.
Yeah, so
these days, there are all these technologies to build a digital twin.
Mm-hmm. Yeah, so we actually have what we call those fast time simulations, and we have one developed at NASA, which we call SOS, Surface Operations Scheduling, and I forget the other, but the idea is that we have this fast time simulator, which we do run these multi-agent fast time simulations to try to understand the impacts of different scheduling approaches or different levels of traffic and stuff like that. There's some other tools that are used in industry. One of them is called AirTop. AirTop can actually integrate the surface with the overhead stream and stuff like that. And so there's all these different fast time simulations. If you were to ask me kind of, I would say that you always have to take the simulations with a grain of salt, because we found just anecdotally here on ATD2 that like for surface metering, there's all these parameters that you should set in order to, meter efficiently. And all the parameters that we found from our simulations when we went to the real operations had to be tweaked and tuned, because of course the real operations are different than the simulation. And where I think is the most different is kind of the level of uncertainty around pushbacks and the pushback process and everything like that.
And SOS has 3D models of airports in it.
We have 2D models of airports with an underlying link node network and everything. And so you can do the full scheduling and everything on it. Yeah.
Well, thank you very much then. Let's thank our speaker. Yep. Thank you for